So the last lesson was arithmetic sequences, which was adding a common difference of d to the last term to get the next term, and so on and so on. In a geometric sequence, which this lesson will be about, we call it a common ratio of r that multiplies the previous term to get the next term. So same sort of idea, except we're multiplying instead of adding. So looking at these sequences, again, these are sequences of numbers. It does follow a pattern. Going from 4 to 12, 12 to 36, 36 to 108, you can probably recognize that the r value here would be 3. We're multiplying by 3. And again, the a value would be 4 in this case, the first term. We use the same variable. Now, in a case like this, it may not be so clear. 270 to 90, 90 to 30. Now, you may be thinking, well, we're dividing by 3. The problem is the r value has to be multiplication. So here's what we can do. Similar to what we did last time, take one number, let's say 90, and instead of subtracting the previous number, we're going to divide. Now, if you do 90 divided by 270, well, some of you are probably thinking 0.33, but it's actually 1 over 3. We want to keep it exact, and we will be using fractions here. So multiplying by 1 over 3 is the pattern. Now, this last one, if you look, 5 to negative 20 to positive 80, negative 320, and so on, well, what would the r value be? Now, you can figure out that going from 5 to 20, well, you're multiplying by 4. But here, you're going from a positive to a negative, and then negative to positive, positive to negative. This actually means that you're multiplying by a negative number. So you're going to see this when the r value is negative, that the signs are going to alternate between positive and negative. Because once you multiply this positive number by negative 4, it becomes negative. But then a negative times a negative is a positive, and so on. All right, so we'll quickly come up with a general formula again. So similar to last time, we use the same notation of this for term 1 is just a. Now, if I want to turn that into term number 2, I'd have to multiply it by r. Now, I'm going to put an exponent of 1 there. We'll see why. Now, if I want to get term 3, I would have to take term number 2, which is ar, and multiply it by r again. But instead of writing a times r, I would write ar squared. That's multiplying by r twice. And just one more, term number 4 would be multiplying that previous term again by r, so ar cubed. Now, very similar to last time, you can see the relationship between the exponent in this case and the term number. So to calculate any term in a geometric sequence, it will be a times r to the power of n minus 1. So 1 less than the term number will be our exponent. That's how many times we have to multiply by r. So very similar to last time, we're just going to use that general formula, and we're going to solve these questions. Now, you may not always be solving for term n. You may be solving for a, or for r, or for n. We'll see what it looks like. So we want to find the 12th term of this sequence. Now, again, we can say that a is equal to 6. And sometimes you can figure out what r is just by looking at it. But you can always take one number and divide by the previous number. So I can say negative 18 divided by 6. Well, r is equal to negative 3. And because I want to figure out the 12th term, I'm going to know that n is 12. That's what I'm going to figure out. So to calculate the 12th term, so term 12, it would be 6 times negative 3. Now notice how that's in brackets. To the power of, the exponent would be n minus 1, or 12 minus 1. And again, I would like you to show me the minus 1 there. Don't just write 11. These answers will get quite large. This is negative 1,062,882. Now, if you think about it, if you keep multiplying by negative 3, multiplying by negative 3, multiplying by negative 3, until you get up to the 12th term, yeah, that's going to become quite large. So our next example here, now we're going to find the 8th term, and I'm not normally going to say this, but we are going to want to keep our answers exact always. So we are using fractions here. Our a value is 1 over 9. Now for the r value, I'll do a little bit of rough work up here in the corner. Now, let's say that I take 4 over 81 as one of my terms, and I can divide that by 2 over 27. Now, how do we divide fractions? Well, we should know how to do this. We've been doing it for a long time. We can multiply by 27 over 2. And I'm going to multiply this on my calculator, but then I'm also going to reduce it. This reduces to 2 over 3. That's our R value right there. Now, you can actually see this in the pattern because the numerator is always multiplied by 2 and the denominator is always multiplied by 3. So my R value is 2 over 3. And again, we're going to be finding the 8th term, so n is equal to 8. So we'll quickly figure this out. The 8th term is equal to, now the a value is 1 over 9 times 2 over 3 to the power of n minus 1 will be 8 minus 1. All right, so I paused the video and I wrote out the solution there. I did show a little bit of process work here just because we're working with fractions, but I do have my answer down here. And we do want to reduce our fractions if possible, but this fraction cannot be reduced, so this would be our final answer. All right, so that was 2 examples finding just what the term is. So how about a question like this? We saw this last time in the sequence 4, 12, 36, ... So that means we're skipping a whole bunch of numbers, and we're ending at 2,125,764. We want to know how many terms are there. So is that the 10th term or the 20th term? We don't know. Now this means that that number is the last term. So I want to figure out what n is for that particular number. Now I've already set up the equation here. So 2,125,764 is equal to 4, that's our a value, times 3. You can clearly see that that's the r value to the power of n minus 1. Now, this may look familiar. This is actually an exponential equation, which we did earlier in the course. So we should know how to solve this. So what we can do is first, I want to get rid of this 4 because we know that for exponential equations, we have to have the same base on both sides. So 3 to the power of n minus 1 is equal to 531,441. So again, we do need the same base on both sides. You can just use trial and error here. So I want to write that large number as 3 to the power of something. So try out some different exponents on your calculator. What you'll find is it is 3 to the power of 12 is equal to 3. Now I really don't need those brackets there. 3 to the power of n minus 1. So at this point, now you can draw an arrow like we did before, or because I have some space on the side, I'll draw my separation here. We now know that 12 is equal to n minus 1. So n is equal to 13. That is the 13th term in that sequence. So same idea as yesterday. You set up the equations and you simply just have to solve for what the unknown variable is. So just make sure you know where everything goes. Last example we'll take a look at. Now this will be the same sort of concept as the last problem we did in the last video, but there's going to be one little twist to it. So given that the third term is negative 48 and the sixth term is negative 3,072, we want to find the first term and the common ratio. Now this time I'm going to skip that step where I write out, T3 equals. I'm just going to write out what the whole equation is. So I'm going to start off with the bigger number. It helps if you start with the bigger number for when you're solving later on. So negative 3,072 is equal to, now because that's the sixth term, I know it's going to be a times r to the power of n minus 1 would be 5. Now the next equation, the third term is negative 48, so negative 48 equals a times r to the power of. Now, because this is the third term, that'll be squared. Now, when we did this question last time, we used elimination. We can't really do that, though, because if we subtract ar to the power of 5 minus ar squared, well, these aren't like terms because they have different exponents. So using the idea of adding or subtracting equations is not going to cut it here. So here's what we can do. We can actually divide the equations. Now, what's going to happen when we do this? Negative 3072 divided by negative 48 will leave us with 64 equals. Now, if we divide these two terms, ar to the power 5 divided by ar squared, the a's are going to divide out. What we're left with is r to the power 5 divided by r squared, and using exponent laws, that will leave us with r cubed. So we know that r cubed is equal to 64, so we've now used elimination except with division. So to figure out r, all I have to do, because I want to eliminate the exponent of 3, I can cube root both sides, and I get an r value of 4. So same idea as elimination last time, except now we are using division. So now I can substitute in that r equals 4 into either one of the equations. It doesn't matter. I'll typically use the smaller one just because it's a little bit easier. So into term number 3, I'll substitute it in. So negative 48 equals a, that's what we're going to try to solve here, times 4 to the power of, now n minus 1 in this case we know is it's squared. So negative 48 equals, now 4 squared is 16, so 16a. And we get our answer, a equals negative 3. So this is what we can do with geometric sequences. Same sort of idea again as arithmetic, just a different equation because there is a different pattern, a multiplication pattern.